Chapter 6, Section 3, Part B. When you go and you look at our equation we just derived in Part A, V naught equals Vmax times the concentration of S divided by our Michaelis constant plus the concentration of S. Take the reciprocal of all that, 1 over V naught. You just flip it over. What was the denominator is now the numerator. And we can go and we can start manipulating further then. You break this down, split this up. Km over S Vmax S. Km over Vmax times S. So same denominator, just separate out the numerators. 1 over V naught equals Km over Vmax times the concentration of S plus 1 over Vmax. If you think about that, that's almost y equals mx plus b. Y equals mx plus b is the equation for a linear line. So if you go and you plot that out, what you end up with is 1 over V naught on the y, and on the x, 1 over concentration. The slope of the line, that if you were to go and plot out the points, slope of the mx plus b, y equals mx plus b, m, now in that equation, the m, the slope, would be the Km. Remember, that's the concentration of S at half Vmax divided by Vmax. Okay? Where y is 0, where that line intercepts, that's 1 over Vmax. Where the line intersects the x-axis, that is negative 1 over Km. So based on this, you could plot out just points. If all you had were data points from a plate reader, concentration of substrate goes down, or as you're increasing it, here's the reaction rate after a given amount of time, and you measure it out and you can plot it out. The initial, and get the V naught, go through, plot it out, and you could come and derive from that the slope of Km over Vmax. Here's Km, here's 1 over Vmax. You could start filling in numbers for Michaelis Menten. The thing is, when you're studying enzymatic reaction rates and you are plotting them out, what you're going to see is they are always hyperbolic. Always hyperbolic, meaning when you plot them out, no matter how steep they start, they will always reach a point where they plateau, curve over, and plateau. And it's dependent on V naught and the concentration of S under the conditions where Km is this and V naught is half max. That half max for each of these is going to be at different places. It all depends on the enzyme, depends on the substrate. Km for varying substrates, enzymes, you look. Beta-galactosidase, lactose, its substrate. Km is 4 millimolar. Carbonic anhydrase, substrate, Km. Hexokinase. Hexokinase is second order, has two substrates, ATP, glucose, fructose. For each of those, again, we have a dissociation constant, like we talked about in chapter 5 when we were discussing hemoglobin, myoglobin interaction with oxygen, and we were looking at, how tight protein ligands are going to bind to each other. Well, we have to have a dissociation here. We cannot have the ES or the EP intermediate so tightly bound that they're not going to release to be E plus P. So you take into account Km, K2 minus K1, divided by K, or K negative 1, divided by K1. The dissociation complex of the ES is something we have to take into account. How we go about calculating that, I'm not going to worry about. Neither should you. PowerPoint doesn't like different versions of the PowerPoint we're using here. So the equation kind of got screwed up. What this should be is arrows this way, arrows that way, not the function. It's not even the function. So when you look at Vmax, you have to take into account many different things. Yes, Vmax is the breakdown of ES to EP. That's the rate of that. That's K2. So we see here, times the total amount of enzyme present, bound and unbound. So when we take into account that E plus S to ES to EP to E plus P, K1, K2, K3. Each of those steps is going to have its own K. Each of it's going to have its own rate. And the reverse of them, K minus 2, K minus 1, so on. But that gets to be a bit much. K1, K2, K3, K minus 1, K minus 2. So we try sometimes to simplify by just saying K-cat, K catalyzed, okay, K catalyzed. If we have a rate limiting, the constant going from ES to E plus S to ES to EP to E plus P, if any of those steps is rate limiting, well, whatever that rate limiting, that's what we call the K-cat. If they are all equal, there's no one, then it is the average across. But we find that the more steps you add into something, into this enzymatic reaction, there's going to be a rate limiting. More steps will become rate limiting, more and more. The complexity becomes too much. So when Vmax and the total enzyme present, when you divide those two, you get the constant rate. So not so much Vmax, but you're taking into account how much enzyme is that totality of the enzyme present, bound, unbound. K-cat times the total enzyme times substrate divided by the Michaelis constant plus S. We think of instead of K-cat, you'll see many biochemists refer to this as the turnover rate. The number of substrate molecules converted to product in a given unit of time on a single enzyme molecule when the enzyme is saturated. Okay, this isn't at the steady state. This just means there's so much more enzyme than there is, so much more substrate than there is enzyme. So that when a product is kicked out, there's automatically another substrate going into the enzyme's active site. So the waiting around is minimized. So, in a given amount of time, how much substrate is turned into product? Catalase. Look at this, catalase, hydrogen peroxide is its substrate. 40 million hydrogen peroxides get turned into water and oxygen. Beta-lactamase, okay? Beta-lactamase is the enzyme produced by bacteria to go and break down any penicillin beta-lactam rings. In a given amount of time, they're doing 2,000 per second. That's just one enzyme. It's cutting 2,000 beta-lactam rings per second. This is turnover. So when you go and you compare our turnover rate divided by our Km, our Michaelis Constant of half Vmax. This is how we can sit there and discuss efficiency. So, V naught, Kcat divided by Km times Et plus S. So what does this mean? Well, if you look at these numbers, numerator, denominator. If our turnover rate is much, much higher than our Km, when we go and we plot out these data points, because this total enzyme, total substrate, okay. Here's where the variability comes into play. If Kcat is much higher than Km, we're going to have a whole number, or hopefully a number approximating or coming close to 1 or way over 1. Our slope of that line is going to be much, much steeper. But when we're looking at V naught, and if Km, Kcat is, our turnover rate is very low, and Km is much higher, our VO, that initial linear line, is going to have a much, much shallower slope. So here's how turnover and our reaction rates come into play. This Kcat times divided by Km has a unit of, molars per second. So when you go and you look at it, enzymes, catalase, hydrogen peroxide, which we talked about. Kcat, 4 times 10 to the 7th, that's the turnover rate. Km, 1.1. So it's ratio 4 times 10 to the 7th. Not bad. Take something like the beta-lactamase. Kcat, 2 times 10 to the 3rd. Km, 2 times 10 to the negative 5th. So this 2 times 10 to the 3rd, that's, doesn't sound like a lot. 2,000, beta-lactam rings per second per enzyme. Not very high when you compare it to like catalase. But look at the Km. The denominator of our ratio is way, way, way smaller. 0.000002. Ooh. So our ratio is 10 to the 8th, 100 million. Yeah, okay. something that doesn't have a very high turnover rate, but its Km is so small that when you look at it, yeah, it's actually quite good. What we find, though, is that not all enzymes are quite as simplistic as we've been talking about with the E plus S to the ES to the E plus P. Turns out there's going to be enzyme plus substrate 1 plus substrate 2 that we have to take into account. What you'll see is a group from one substrate is transferred to another. Cut off a methyl, transfer it. Cut off a carboxyl, transfer it. Or one substrate is oxidized, the other is reduced. So now you have to take into account E plus S1, ES1, in comes S2, ES1, S2, EP1, EP2, kick out product 1, EP2, E plus 2. This is if everything has a nice, logical, as it says, ordered. But then it gets worse. It's random. Sometimes it's random. Who gets in first? S1 or S2? At some point in time, you're going to have both of them in there. Here, an ordered ES1 is now available for S2. The enzyme without the S1 there first, it's not going to interact with S2, even though it will at some point, but only if S1 is already there. This random order, hey, as long as both of them get in there at some point in time, that's all that counts. And sometimes you see that we don't have, even if there's going to be multiple substrates, it's not a E plus S1, ES1, now you have ES2 like we saw, the ordered, or even the random E plus S2, ES2, now we bring in S1. Now sometimes it's, as we see here, E plus S1 gives you product 1, kicks out, but now you have E prime. E prime is the enzyme, and it has retained the electron for a redox reaction. It has retained a functional group. It has retained something that now needs to be transferred to the next substrate. After it transfers over, E prime S2, you now have E plus product 2. Oh. So because of this, we got to have nomenclature. We got to have a means of discussing these things. So they call this the Cleland nomenclature. It's a shorthand notation. You have different substrates, A, B, C, D. Okay, it's much easier than sitting there saying substrate S1, S2, S3, S4, whatever. And then products, QRST. And you go through and you label them. Both the substrates and product are labeled A, B, C, D, P, Q, R, S, T, based on who comes first. First substrate, A, second, B, third, C, and so on. First product, Q, first product, P, second product, Q, S, T. Okay. And how many substrates are going to be made? Is it uni? Is it bi, ter, quad, whatever? We'll see that if the enzyme is modified during the reactions, remember previous slide, the E prime or anything like that, then it becomes F, then it becomes G, so on, as different things are occurring to it. So if you have what is referred to as a bi-bi reaction, enzyme E takes on A, becomes EA, brings in substrate B, you now have EAB. A and B get changed to PQ. P is the first to be released, Q is the second. Now you have the enzyme free, ready to do it all again. Okay, that's similar to what we saw with the ordered, but instead of ES1, ES1, bring in S2, ES1, ES2, we're now referring to them as AB, PQ. This random bye-bye, same thing as we saw before. Just got rid of the S1s and S2s and the P1s and the P2s. This also allows you to bring in what is referred to as the ping pong. E brings in A. You have this intermediate EA. EA forms P. But the thing is, during this, the enzyme gets modified. It picks up an electron from a redox reaction, some form of a functional group or something to be added on to somebody else. P is now released. It's been oxidized, or it's had a methyl group removed, or whatever. The enzyme is now F, with a little something extra waiting in its active site. Substrate B comes in. You now have FB. F transfers over that electron, that functional group, that whatever it was retaining. Adds it to B. B now becomes Q. F, since it no longer has that whatever in its active site waiting, reverts back to E. Q's released. You now have E free and ready to go. So we can take and look at the Michaelis constant, and where before we were looking at it as a monosubstrate, we can look at it as a bisubstrate. A and B, or S1 and S2, whichever way you want to think of these. So if you map it out, 1 over V0, 1 over S1, like we talked about before, and you looked at the initial, the slope of this was Km over V max. If you have something that is E plus S1 and at some point in time S2, or E plus A and sometimes later B, the rate is actually, this is going to become more and more shallow as you increase this. Because remember, this is, looking at the reaction rates. If it's a ping pong, double displacement, you'll see that the lines don't all have the same V0. Now, as you increase the S2, the second substrate, they actually shift to the right. In a sense, decreasing 1 over V0. And as we've talked about previously, you've seen it in this course and other courses, enzymes, because of their tertiary quaternary structure and how everything's are held together, pH is going to play a really big role in enzymatic activity. Here you look at pepsin and glucose 6-phosphate. Pepsin, which is the protease that's in our gastric juices that helps digest, break down proteins in your stomach. Stomach's going to be about a pH of 2. So its optimal, its highest point of activity is going to be right there around pH 2. As the pH goes up, well, pepsin activity is going to go down as it is denatured. Take something like glucose 6-phosphate, which works best in our cell's cytoplasm. Okay, cytoplasm of a cell is going to be a little more basic than the blood, way more basic. Couple, what is that? 2 to the 8, so that's 6, 10 to the 6. So that's 1,000,000 times more basic than the stomach. More alkaline. Too hot, too cold, right here, just right. Well, you can go and you can study this. There are mechanisms for studying this. You have different equipment, different things that you can go through, and you can add in a steady rate of enzyme and substrate together. So instead of just mixing it all at once, you can increase, decrease the addition of enzymes and substrate into a reaction volume, and then you can measure product being made depending upon how much and how quickly the flow of E in the S is occurring. So, for an enzyme where product release, EP plus EP is rate limiting. So that's the K3 step. We see that the K3 limits just how fast the enzyme can reset to become free enzyme and take up more substrate. And you can go and you can calculate this out by looking at, what happens over time if we have we measure the product and we increase enzyme. So before, we've been increasing and decreasing substrate levels. Well, here we're going to ignore substrate levels and we're just going to look at increasing enzyme and increasing the product, or measuring the increased product over time. And we're going to sit there and try to calculate out what's the rate limiting. At what point are we saturating? At what point have we hit everything we can? The observation of a burst indicates that a rate limiting step, product release, enzyme conformational changing back to its free state, occurs after formation of the product being monitored. So we go and we look and we can calculate from this and we can figure out just how this works.